Alright, so if you guys are back, I appreciate you coming back to learn how to do the rest of these, or just check yourself on the rest of these and see, maybe learn a new method, possibly. Because I know mine isn't always the exact method you were taught, so it's good to have multiple ways to do stuff. Anyways, I've wasted 30 seconds of your time about this, so let's just get into it, since you listened to me babble last time too. Alright. So, okay, verse 17. We're going to write a balanced equation for the reaction between aqueous, so that's going to tell us the state right there. AQ, lead to nitrate, and aqueous, there's another state. Potassium chloride to form solid lead 2 chloride, so there's another state for us. And aqueous potassium nitrate. So, when I'm reading these, to tell how I'm even going to set it up, what's going to go where, we're talking about the reaction between this and this. So keywords in this. First reaction, of course, between, this would be our compound number 1. The and is going to be the plus sign. Compound number 2 would be this guy right here. And then to form, that's going to be our arrow. And then, again, this is going to be another compound right here, lead 2 chloride, and another plus sign, and then another compound here, potassium nitrate. So, let's break this down over here. Increase the brush size a little bit. Hopefully you guys can see that. So our first compound is going to be aqueous lead 2 nitrate. So we have Pb2 plus and NO3 minus. So when we put those compounds together, we're going to get Pb NO3 2 aqueous. The next one is going to be potassium chloride. So we have K plus Cl minus. So that's going to be KCl. That's going to be aqueous. So far we have Pb NO3 2 AQ plus KCl AQ, and remember those react to form, so arrow. And then we have lead 2 chloride, so we have Pb2 plus Cl minus. When we swap charges, we get PbCl2, and we're told that that's a solid, so blank PbCl2s plus, and K plus and NO3 minus, potassium nitrate, so KNO3, so plus KNO3 aqueous. So when I'm doing these, my preference is to go and write what I have. So I have Pb, I have NO3. If you can keep your polyatomics together, do that. It's going to save you so much. We have K and we have Cl. So when we go ahead and go along and put these in, actually, give me like 2 seconds. Let me fix this that I'm doing here. Okay, so we have Pb, NO3, K, and then Cl. So on this side of the reaction, we have 1 lead, 2 nitrate, 1 potassium, 1 chloride. On this side, we have 1 lead, 2 chloride, 1 potassium, 1 nitrate. So to balance these, I would do this. I would go ahead and see, what do we need to do first? Let's put a 2 right here. So that's going to boost that up to 2, that up to 2. And then looks like we need 2 chlorine over here. That boosts that up to 2, and that up to 2. So 1, 1, 2, 2, 2, 2, 2, 2. Perfect. Looks like we're good there. So our balanced reaction would actually be PbNO3 2. Oh gosh. So PbNO3 2 aqueous plus 2 KCl aqueous to form PbCl2 solid plus 2 KNO3 aqueous. And looks like we are good there. So, wow, that looks horrible when you zoom in on it. But, yes, PbNO3 2 aqueous. Wow, that is really bad. Sorry. 2 KCl, 1 PbCl2, and then 2 KNO3. Perfect. So that's how I approach those though, is I like to do the thing in the middle, where I write everything that I have and start adding it up on both sides. And you'll see that I do that, like if you go to the SI sessions, that's my go-to method right there. Alright. So balancing the following reaction, we're gonna go ahead and do pretty much the same thing we just did. Not pretty much, exactly the same thing we just did. So first thing I would do is rewrite the equation. B2O3. Don't worry so much about the states, because you really just need the numbers that are going to go in front. So that'll save you a couple seconds of writing. BF3 plus blank H2O. So we have BOHF. So on this side we have 2 boron, 3 oxygen, 1 hydrogen, 1 fluorine. Over here we have 1 boron, 3 fluorine, 2 hydrogen, 1 oxygen. So what I tried to do is leave the ones that are by themselves for last, if it's at all possible. So in this case, there's only 1 and 1 of each, so I'll be able to just put whatever number I need to in front of this. So, oxygen, I know I need at least 3 oxygen, right? So let's go ahead and put a 3 here. Remember, that doesn't just change the oxygen, that changes the hydrogen as well. That boosts that up to 6. So we have 3 and 3. Now for fluorine, I know I need at least 3. Oh, here, let's do boron. Put a 2 in front of this. That puts that up to 2, and that changes this to 6. Well, now you can see why I leave this by itself, because if we started doing hydrogen, then I would have put 2, but I would have had to change it. You look here, for H and F, I just need 6. So I'm going to drop a 6 right there. And then put 1 right here. Let's go ahead and do a quick check. 2, 2, 3 oxygen, 3 times 1 is 3, 6 hydrogen, 3 times 2 is 6, 6 fluorine, 2 times 3 is 6. Perfect. So the coefficients are 1, 6, 2, 3. Wow, that was a bad circle. Oh well, you get the point. Alright, balance the following reaction. So this one is one of the ones that if you look at the combustion reactions, those are the ones that tend to like get a little messy. So let's do this one off to the side. Let me go ahead and get rid of this stuff really quick. All right. So we have blank C6H6 plus blank O2. When you're doing these, save oxygen for last, like undoubtedly, because that is, whenever you have something by itself, it's a lot easier to just go ahead and save that for last. Okay, so this one's actually really easy to set up on the right side, because if you have H2O and CO2, that's just 1, 2, 3, right? 1 carbon, 3 oxygen, 2 hydrogen. Over here we have 6, 6, and 2. So let's go ahead and start. Let's balance our carbon first. Let's drop a 6 right here. It doesn't matter if you do the carbon or hydrogen first. Just, again, save the oxygen for last. Alright, so that boosts that to 6. That makes this 6 times 2 is 12 plus 1, 13. So we need 6 hydrogen, so we're going to drop a 3 right there. That turns that into 6, and this into 15, right? It's 12, 13, 14, 15. Okay, so this is going to remain unchanged for now. And it looks like for our oxygen, we need 15 total, so 15 over 2. So in order to do this, if you have a fraction right here, whatever number you need, just put it over the 2. And then you'll see you can't have a fraction, so we're going to multiply this whole thing here by 2. And that's going to give us the new coefficients of 2, 15, 6, and 12. So let's do a total here and make sure we're good. Alright, 6 times 2 is 12, 12, 30. 6 times 2 is 12. 12 times 1 is 12. And then 12 times 2 is 24, plus 6, 30. Everything checks out. So our coefficients here would be 2, 15, 6, and 12. I highly recommend trying a few of these until you get really good at these. Sometimes they take a little bit of thought, but they seem to, once you get the hang of it, you're pretty good. Okay, so which one describes a combustion reaction? So, combustion reactions are generally CX, HY, OZ, though the O doesn't always have to be there, plus O2 to give us CO2 plus H2O. So if we look, this does not have any H2O or CO2, nor does this, nor does this. This has H2O, but no CO2. This one has CO2 and H2O, so that's it right there. And then, yeah, so that's that one. Let's go through and classify the rest of these. This bad boy right here, what would you guys call that? It actually has 2 names. It can be a neutralization reaction, IZATION. That's like the more correct name for it, but the other name for that, it's also a double replacement reaction. It's a special double replacement reaction between an acid, in this case nitric acid, and a base, in this case lithium hydroxide. And it's an acid and a base come together to form a salt, in this case lithium nitrate, and water, in this case water. I know, that was ridiculous. I'm sorry. This guy right here. So for a general reaction, it would look like this. A plus B is coming together to give you AB. So this would be a combination. So for, hold on one second, sorry. Sorry for that again. Okay, so we were right here. Okay. Sorry, she has like fever of 103, so probably gonna go to the emergency room soon. Let's finish this up. Okay. So right here, this reaction would look like this. You have A plus BC as a general reaction. That is going to AC plus B. So that would be a single replacement reaction. And then for this one right here, we've got the same deal. We have A plus BC going to AC plus B. So again, that's a single replacement. She did say to make sure you guys know how to do that. So I would, on your note card, if you aren't comfortable with recognizing what kind of reactions, I would write the general terms for it. So like I did here, A plus BC, or A plus B gives you AB, or AB plus CD gives you AD plus CB. That would be double replacement. Okay, number 21. Oh my gosh. Okay, so here we have this substance, dimethylnitrosamine. Nitrosamine, yeah. It's a carcinogenic substance that may be formed from a reaction that takes place in food preservatives. How many molecules of this are in 1.75 milligrams of dimethylnitrosamine? So we're going to need to find out the molar mass of this. So we have 2 times 12.011. For hydrogen, we have 6 times the molar mass of hydrogen, 1.00794. We have for nitrogen 2 times 14.007, and for oxygen 15.9994. When we add all of this together, we get the molar mass of 74.08304 grams per mole. And we want to know how many molecules are in 1.75 milligrams. So we need to convert this into grams. So 1.75 milligrams times 1,000 milligrams in every gram is going to give us 0.00175 grams of our substance. So let's go ahead and do the math on that really quick. We have 0.00175 grams. I'm just going to put D for dimethylnitrosamine, times our molar mass, which is 74.08304 grams of D for every 1 mole of D. And then to go from moles to molecules, we know that 1 mole D is going to be 6.022 times 10 to the 23 molecules of D. So when we do that math, we get 1.4225, and it keeps going, times 10 to the 19, that's a 9 molecules, which, to the correct number of sig figs, 3 sig figs, is 1.42 times 10 to the 19 molecules, D, which would give us this answer right here, A. Alright, number 22. Determine the theoretical yield in grams of aluminum hydroxide if this many grams of aluminum sulfide reacted with this many grams of water, and then find, or according to the following reaction. Oh my gosh, I forgot to do the water part. Okay, so I'm going to have to do a little bit of math here. So 31.1, whoops, started with the answer. 30.0 grams of Al2S3. Alright, here's why I only did the math on one of them. If you look, you're starting with 30 grams of both. So the molar mass of aluminum sulfide is 150.1581 grams per mole. Of water, it's only 18. So just using some logic here, we can find out that there's going to be less moles of aluminum sulfide than there is of water, right? We're going to have over 1 mole of water, but we're going to have far less than 1 mole of aluminum sulfide. So we don't even have to do the math for the water. If they're close on masses, I would do the math just to be safe, but in this case they're so far apart that you can just go ahead and just go for it. Just do the one that's obviously going to give you less moles. So we want to find out aluminum hydroxide. So it's 150.1581 grams of Al2S3 and 1 mole of Al2S3 times, for every 1 mole of Al2S3, that's coming from right here, we will get 2 moles of AlOH3. Now, using the molar mass of this, we can find out how many grams we're going to get. So 1 mole of AlOH3 is 78.0036 grams of AlOH3. And when you do the math on this, you get 31.168 grams of AlOH3, which to the correct number of sig figs is 31.2 grams of AlOH3. Now you can go through and do the math. What would change is this would say 30.0 grams of H2O, 18.015 to 8 grams of H2O, or 1 mole H2O. And then if you look here, it's also going to say 6 moles of H2O, that's from right here, to the 2 moles of AlOH3. That's a 1/3 ratio. So it's going to work out to be even less in this case. Or not even less. It's going to work out not in your favor in this case. So let's just do the math. I'm already pretty much there. So 30.0 divided by 18.0152 equals times 2/6 equals times 78.0036 equals, so when you do the math on this one, sorry about the size of this and how cluttered it is, 2987. So you would get this mass. This is far less than that. So that would be your correct answer. If you look, if you just did water, that answer shows up here, but it's not right, because this is less than that. Okay, almost there, guys. Stick with me. We have two more? Cool. 23. Okay, iron 3 oxide reacts with aluminum to produce aluminum oxide and iron. So iron 3 oxide, that's Fe3 plus O2 minus plus Al to produce Al3 plus O2 minus plus Fe. So to write the formula correctly, would be Fe2O3 plus Al to give me Al2O3. That puts a 2 in front of here, plus 2 Fe. Right, so 3 oxygen, 2 aluminum, 2 aluminum, 2 iron, 2 iron. Perfect. If that's our actual yield, when this much iron 3 oxide reacts with excess aluminum, so we don't have to worry about the aluminum, what is the percent yield? Okay, so 50.00 grams of Fe2O3 times the molar mass, which is going to be 2 times Fe plus 3 times oxygen. When you do that math, you will get a mass of 159.6922 grams per mole. So 159.6922 grams of Fe2O3 and 1 mole of Fe2O3 times, for every 1 mole of Fe2O3, we get same color, 2 moles of Fe, and then 1 mole of Fe is, or iron I guess I should say, it's 55.847 grams of iron. When you do the math, unit canceling, cancel, 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 you get 34.97165 grams of Fe. They're saying that we actually got this mass. So, we didn't do so well, I don't think. Oh, no, we did pretty well. So, to find out the percent yield, that is going to be 28.65 grams of Fe divided by, so it's actual divided by theoretical times 100%. Our theoretical will be what we just calculated. That's going to be 34.97 grams of Fe. So our percent yield is going to be 81.92349688%, and then to 4 sig figs, 92%. That will be our percent yield. Alright. Sorry, I know it seems like I'm rushing through this. Just a little worried. Okay, so which one does not match? Another one of these lovely questions. Alright, so barium nitrite. So barium is Ba2+, right? And then nitrite is NO2-. So when we put those together, we're going to get BaNO2 2. That checks out. Alright, iron 3 hypochlorite. Okay, so we have Fe3 plus hypochlorite. That's going to be ClO-. When we put those together, we should get FeClO3. Well, we've got something extra right there that we don't need. So that would be our answer right there. Just to make sure that we are 100% correct. Titanium 2 carbonate. That's Ti2 plus, CO3 2 minus. And we have a heptahydrate, hepta meaning 7, and hydrate meaning H2O. Put those together, we get TiCO3 dot 7H2O. Checkity check check. And tin 4 fluoride, we have, I did this last time too. It's SN4 plus, F minus. So when we put those together, it's SNF4. Checks out. And our last guy over here, lead 2 phosphate. So peanut butter 2 plus. Phosphate is PO4 3 minus. Let's go ahead and do a swap of the charge. You gotta make the noises or it didn't really happen. We have PB3, PO4 2, and that checks out. Sweet. So thanks for sticking around through everything. I know there's a lot of breaks and stuff. Sorry about that. I hope this helps at least a little bit. Let me know if you have any questions on any of this. And yeah, I look forward to hearing from you guys. Take it easy.